Welcome back to Mechanical Engineering Made Simple Legends. I'm your host. Be water, my friends, or drown in the math. Today we crack fluid mechanics, the subject professors pitched as a lazy river but delivered like a tsunami. Bruce Lee got it right. Water flows or it crashes. Bottle it. It becomes the bottle. Bad equation. Instant nightmare. Be water, whatever the hell I just butchered. I think I just improved the quote. Rough pipe. Drag city. Reynolds number. The bouncer at the door. Screw it up and cavitation eats your lunch. Stick around, learn to dodge the water hammers, reality hurls like fastballs. Master the valve before it leaks worse than a campaign promise. Be water, my friends, or get washed away, rookie. Class. In. Session.
Wow. Yeah, that is quite the syllabus today, but I mean, it's vital, and we are really stripping away the academic fluff here to look at the fundamental laws that dictate how, every fluid interacts with our built environment.
Yeah, and that is exactly the entire mission of this deep dive. Because look, we have compiled a massive stack of textbook data, engineering failure reports, theoretical models, but
we're not just going to sit here and read equations at you.
right. Exactly. We are here to deliver a hard-hitting, practical lesson designed specifically for you. The engineer actually trying to survive real-world design challenges.
Yeah.
We're covering the crucial rules of fluid statics, the destructive power of unsteady flows like water hammer, which is terrifying, the sticky reality of viscous pipes, open channel nightmares, and the brutal fixes of drag, lift, and cavitation.
But before we dive in, let's establish the ground rules here. There are no pretty promises today.
Nope.
We are dealing strictly with the math and the physics that govern reality. Fluid mechanics, it doesn't care about your deadlines. It doesn't care about your budget or your architectural vision.
It really doesn't.
If you ignore these principles, your pipes burst. Your pumps will literally dissolve themselves from the inside out, and your structures fail catastrophically.
It's unforgiving. So let's start the very beginning. Because before a fluid even starts moving and causing all that chaos, it is already laying traps for the unwary designer just by sitting there. I'm talking about the invisible weight of fluid statics, the trap of pressure.
Right, and the very first trap you'll encounter in the field is just a fundamental misunderstanding of how we measure pressure itself.
Okay, lay it out for us.
Well, we have to clearly separate absolute pressure from gauge pressure. Absolute pressure is measured relative to a perfect vacuum. So zero absolute pressure means there's absolutely nothing there, like the vacuum of big space.
Right.
Gauge pressure, however, is simply absolute pressure minus the local atmospheric pressure.
Because we live at the bottom of an ocean of air.
Exactly.
The air is constantly pushing down on us with a pressure of roughly 101,325 pascals, or,
Right.
one standard atmosphere. So if I leave a pressure gauge sitting on my workbench, it reads 0.
Right.
But it's not that there's no pressure there, it's just calibrated to ignore the weight of the sky.
Which leads to one of the most common and honestly most dangerous pain points for young engineers. The mistake is specifying the wrong pressure sensor type for a sealed system.
Oh, I've seen this happen.
Yeah. Imagine you design a sealed industrial chemical tank. You specify a gauge pressure sensor when the math actually required an absolute pressure sensor.
Big mistake.
Huge. So you might start pumping fluid out of that tank, you watch the gauge pressure drop towards 0, and you think, okay, great, everything is fine.
But because you are using a gauge sensor, your quote-unquote 0 just means you've reached atmospheric pressure.
Exactly.
And if you keep pumping, that needle drops below 0. You haven't just emptied the tank, you've created a negative gauge pressure, a vacuum inside it.
And here's where reality hits hard. If that tank was designed to hold pressure from the inside pushing out, but it was never structurally reinforced to withstand external atmospheric pressure crushing inward.
It implodes.
It implodes. It folds up like an aluminum soda can.
This crunches.
Yes. That is a terrifying reality check for a lot of engineers. You have to know what your 0 point actually means in the physical world.
It really emphasizes why we need to understand the baseline physics before we draw a single line in a CAD program. Which I guess brings us to Pascal's law. This is kind of the magic trick of fluid statics, isn't it?
It is. Pascal's law basically states that pressure applied to an enclosed fluid is transmitted undiminished to every part of the fluid and to the walls of its container.
Undiminished.
Right. And this is the entire basis for heavy machinery, the hydraulic press, the brakes in your car, the massive actuators on an excavator.
And the underlying logic here is just brilliant. Pressure is simply force divided by area. And because the fluid is incompressible and it's enclosed, that pressure has to remain constant everywhere inside the system.
Right.
So if you have a tiny piston connected by a tube to a massive piston, the math says force 2 equals force 1 multiplied by the ratio of area 2 to area 1.
Exactly. It's a force multiplier.
You push down with a small force on a small piston, and the fluid transmits that pressure to the massive piston, creating this massive output force. You can lift a 2-ton truck with the push of a finger.
But, physics always demands a trade-off.
Right. There's no free lunch.
Exactly. Energy must be conserved. So to get that massive output force, you sacrifice distance. You have to push that small piston a vastly longer distance just to move the large piston even a fraction of an inch.
Makes sense. But that is for an enclosed fluid where we are actively applying external mechanical pressure. What about a fluid just sitting open to the sky, like a reservoir or the ocean?
Well, there, we have to consider how pressure variations scale with depth.
Because the deeper you go, the heavier the water above you gets.
Right. The relationship is a simple linear buildup. The pressure at any depth relies on a really straightforward calculation. You take the pressure at the surface, which is usually just atmospheric pressure, and you add the weight of the fluid column above you.
And that weight is dictated by the fluid's density, the pull of gravity, and the total depth.
Yep. And that linear relationship is incredibly powerful. It tells us that pressure inside a liquid increases strictly in proportion to depth. It does not matter if you are at the bottom of a pipe that is 1 inch wide or at the bottom of a lake that is 5 miles wide.
Wait, really? The width doesn't matter at all?
Not at all. If you are 10 meters down in fresh water, the pressure squeezing in on you is exactly the same in both cases. The total volume of water around you doesn't matter. Only the vertical column of water directly above you matters.
That's wild to think about, which leads to how we actually measure these pressure differences out in the field. Let's talk about manometers, like the classic U-tube manometer.
Oh, yeah. It's wonderfully simple. You just have a glass tube shaped like a U filled with a heavy liquid, usually something like mercury.
Right.
You connect one end to your pressurized pipe, leave the other end open to the atmosphere, and the pressure in the pipe physically pushes the mercury down on one side, forcing it up on the other.
And you just take a ruler and measure the height difference between the two columns?
It is brilliant in its simplicity. But what if the pressure change you need to measure is microscopic? Say you are measuring the draft in a low-velocity HVAC duct.
Okay.
A standard vertical U-tube might only show like a millimeter of movement, which is impossible to read accurately with the human eye.
So we cheat gravity, the inclined manometer.
Exactly. We take one leg of that U-tube and we tilt it to a shallow angle, say 10 or 20 degrees. Now, when that tiny pressure pushes the liquid down on the vertical side, the liquid on the tilted side has to travel a long physical distance up the slope just to gain a tiny bit of vertical elevation.
Oh, wow. So 1 millimeter vertical change might translate to a 10 centimeter diagonal movement along the glass tube.
Right. You have effectively created a mechanical amplifier for your eyeballs using basic trigonometry.
I love that. But let's be real, you aren't going to have fragile glass tubes full of toxic mercury strapped to the side of a vibrating diesel engine on a job site.
No, absolutely not. For industrial applications, we use elastic deformation to measure pressure, specifically the Bourdon tube. It's everywhere.
Yeah, that classic dial pressure gauge on an air compressor or a welder.
Right. And the mechanism inside a Bourdon tube is fascinating. It's essentially a flattened metal tube that has been bent into a C-shape, or sometimes a coil.
Okay.
When pressurized fluid enters the tube, the internal pressure pushes against the flattened walls, trying to force the tube back into a perfect circle. And as the cross-section tries to round out, the entire C-shape naturally tries to uncoil and straighten.
It's exactly like those paper party blowouts you get at birthdays. You blow air in, it unrolls.
That is the perfect analogy. And in the gauge, the tip of that uncoiling metal tube is hooked up to a tiny gear train that spins the needle on the dial.
Simple but bulletproof.
Yeah, but modern systems take this a step further with diaphragm gauges. Instead of a curving tube, the pressure pushes against a flexible metal membrane.
Like a drumhead.
Exactly. And as the membrane bulges under pressure, microscopic strain gauges bonded to its surface stretch, which changes their electrical resistance. This allows us to convert physical pressure directly into an electronic signal.
Which is essential for measuring rapidly fluctuating pressures in, like, digital control systems.
Absolutely. You need that instantaneous data.
Okay, let's shift from the instruments back to the fluid itself and look at the forces a static fluid exerts on massive submerged objects. This brings us to the bathtub, Archimedes, and the concept of buoyancy.
Ah, yes. The legend of Archimedes realizing that a body immersed in a fluid experiences an upward buoyant force equal to the weight of the fluid it displaces. It's foundational.
Right. When a ship sits in the water, it carves out a hole in the ocean.
And the ocean wants to fill that hole back in, so it pushes upward.
And the center of gravity of that invisible displaced volume of water is what we call the center of buoyancy. But simply floating isn't the whole job, is it?
Not at all.
A floating object must be stable. If a ship floats but flips upside down the moment a seagull lands on it, well, it's a terrible ship.
Right, which introduces the critical concept of the metacenter. Imagine a ship sitting perfectly level on calm water. Gravity is pulling straight down through the ship's center of gravity, and buoyancy is pushing straight up through the center of buoyancy along the exact same vertical line. Everything is in perfect equilibrium.
But the ocean is never calm. Let's say a massive wave hits the side of the hull, and the ship rolls 30 degrees to starboard.
Okay, when the ship rolls, the physical shape of the underwater hull changes. The right side is pushed deeper into the water, and the left side lifts out.
Right.
Because the shape of the submerged volume has changed, the center of buoyancy physically shifts over to the right.
So the buoyant force is no longer pushing straight up through the center of the ship.
Exactly. Now, if you draw a new vertical line straight up from this shifted center of buoyancy, the point where that new line intersects the ship's original central vertical axis is called the metacenter.
Okay, got it.
And the absolute golden rule for maritime stability is that this metacenter must be located above the ship's center of gravity.
Wait, why?
Because if the metacenter is above the center of gravity, you have gravity pulling down on the center of the ship and buoyancy pushing up on the side that's submerged. This creates a restoring couple, a rotational torque, that naturally tries to twist the ship back to a level, upright position. The ship saves itself.
Oh, that makes sense.
But if the metacenter is below the center of gravity, that torque acts in the opposite direction. It actively pushes the ship further into the roll. The ship capsizes. The distance between the center of gravity and the metacenter is known as the metacentric height.
Okay, wait, let me stop you there, because the data on metacentric heights threw me for a loop.
How so?
If a high metacenter means a massive restoring force and extreme safety from capsizing, then a massive floating city like a cruise ship should have the highest possible metacenter, right?
I would think so.
But the numbers show warships have metacentric heights around 1.2 meters, while giant passenger ships are only around half a meter. That feels totally backward. Why make the civilian ship less stable?
It seems counterintuitive until you look at the human element of engineering. You are entirely correct that a high metacentric height means the ship is vastly more resistant to capsizing. But naval architects refer to a ship with a high metacenter as stiff. Yeah, when a stiff ship rolls in a wave, that massive, powerful restoring force snaps it back to the vertical position incredibly violently. The ship aggressively rights itself.
Oh.
If you put thousands of tourists on a stiff ship, that fast, jerky, violent snapping motion would subject them to immense lateral G-forces. They would be violently seasick before they even reach the buffet.
Ah. So a passenger ship is intentionally designed to be what they call tender.
Exactly. It has a lower metacenter, so the restoring force is weaker. When a wave hits it, it rolls slowly, and it rights itself slowly and gently. You sacrifice a margin of ultimate extreme weather stability to ensure the passengers aren't thrown out of their deck chairs.
You engineer for the use case?
Precisely. A warship, conversely, does not care about passenger comfort. A warship needs to provide a highly stable, level platform for its radar and weapon systems to calculate firing arcs. If a wave rolls a destroyer, it needs to snap back to dead level immediately so the guns can stay on target.
That is fascinating. The physics are dictated by the mission. Okay. Keeping with the destructive forces exerted by static fluids, there is a massive trap waiting for civil engineers designing underwater structures, like a dam or a steel sluice gate.
Oh, definitely. We are talking about the difference between the geometric centroid and the true center of pressure.
Right. So if you are an engineer looking at a flat, rectangular steel gate holding back 20 feet of water in a reservoir, you might calculate the total force of that water. And the rookie mistake is assuming that because the gate is a perfect rectangle, the force of the water pushes dead center on the gate, right on the geometric centroid.
And it is a fatal assumption. You have to remember the fundamental rule we discussed earlier. Pressure increases linearly with depth.
Right. The deeper you go, the heavier it gets.
Exactly. So the pressure of the water at the top of the gate is relatively low, but the pressure at the very bottom of the gate is immense.
So the pressure distribution isn't a flat square, it's a triangle, getting wider and heavier at the bottom.
Yes. And because the bottom of the gate is being pushed significantly harder than the top, the effective point where all that distributed force is mathematically concentrated at the center of pressure is always pushed lower than the geometric centroid. It is never in the middle.
So if you design the structural hinges for that gate, assuming the massive force of the reservoir is hitting the middle, but the real force is actually concentrated much lower down.
Your torque calculations are completely wrong.
Wow.
The hinges will experience a massive twisting, bending moment that you never accounted for. The steel shears, the gate blows out, and you have a catastrophic flood on your hands.
That is the unforgiving nature of fluid statics. Even when water is doing absolutely nothing, its sheer, uneven weight is waiting for you to make a geometric error.
It really is.
But we've established that fluids at rest follow predictable, if dangerous, rules. But what happens when you force that fluid to move and then try to stop it abruptly?
Well, then the physics shift from predictable weight to violently destructive shock waves.
Right. This brings us to unsteady flow and the absolute nightmare phenomenon of water hammer.
We are moving from statics to dynamics now. Specifically, the mechanics of instantaneous valve closure. Imagine a long, heavy industrial pipeline moving thousands of gallons of water a minute. At the end of that pipeline is a massive shut-off valve. And for whatever reason, a power failure. A safety trip, that valve slams shut instantly.
The fluid's velocity drops from high speed to absolutely zero in a fraction of a second.
Exactly. And here's where a widespread simplification taught in engineering schools proves fatal in the real world.
What's that?
To make the math easier on paper, we often treat liquids as perfectly incompressible. And for steady, everyday flow, assuming water cannot be compressed is a perfectly fine approximation. But under extreme kinetic shock, that assumption is a lie.
Oh, wow. So it actually compresses.
Yes. When that valve slams shut, the momentum of thousands of pounds of moving water has to go somewhere. The water right at the closed valve stops, but the water a mile back up the pipe is still moving at full speed, crashing into the stopped water.
It's like a multi-car pileup on a highway. The front car hits the wall, and the cars behind it smash into the front car.
Perfect analogy. The fluid physically compresses, packing in on itself, and the steel walls of the pipe are forced to bulge outward to accommodate it. The kinetic energy of the flow is instantaneously converted into a massive localized pressure spike.
But that pressure spike can't just stay at the valve, right?
No, it rebounds. It propagates upstream, away from the valve, exactly like a shock wave. And the speed at which this destructive wave travels is the speed of sound in that specific fluid pipe system.
And the math here reveals something wild. The speed of that shock wave relies entirely on a tug-of-war between how dense the fluid is and how elastic both the water and the pipe wall are. The stiffer the pipe, the faster and more destructive the wave.
We calculate this wave speed using a modified bulk modulus.
Okay, break that down for us.
The regular bulk modulus tells you how compressible the fluid itself is. But because the intense pressure wave also expands the pipe wall outward, the fluid effectively acts even more compressible than it really is. We have to account for the elasticity of the steel or the concrete.
Okay, so how fast are we talking?
In a typical municipal water main, this high-pressure shock wave rips up the pipe at speeds between 600 and 1,200 meters per second.
That's insane. Let's put that in perspective for you. If I'm driving a car at 60 miles an hour and hit a brick wall, the metal of the car crumples, absorbing the energy. But if a massive column of water in a pipe hits a suddenly closed valve, the water cannot crumple.
Right.
The pipe cannot crumple. So the kinetic energy blasts outward into the pipe wall itself. It is literally a supersonic shockwave firing backwards through your plumbing.
And the magnitude of that initial pressure spike is brutal. You calculate the change in pressure by multiplying the fluid's density by the initial flow velocity and multiplying that by the massive wave speed. This shock wave can easily generate internal pressures 10, 20, or 30 times higher than the normal operating pressure of the pipeline.
And the nightmare doesn't end after one hit, does it? The wave bounces.
It bounces. It travels all the way upstream until it hits a reservoir or an open tank. Once it hits the open tank, the high pressure suddenly relieves itself into the open space. But nature overcorrects.
What happens?
A low-pressure wave then reflects and travels all the way back down the pipe to the closed valve. The fluid rushes back in, slams into the closed valve a second time, and the cycle repeats. The pipe is hit over and over again until friction finally dampens the energy.
So the critical timing here is the wave's round-trip time. The time it takes the wave to travel from the valve to the reservoir and back. If your valve closes faster than that round-trip time, the fluid experiences it as an instantaneous closure, and you get the maximum possible pressure spike.
Exactly. To prevent your system from blowing apart, you must control the closure time. If you close the valve much slower than that round-trip time, the initial pressure wave has time to travel up, reflect, and come back as a low-pressure wave.
Oh, I see.
Yeah, that returning low-pressure wave meets the still closing valve and counteracts the pressure that is currently building up, canceling out the worst of the spike.
And the textbook data cites Alivi's equation for this. Lorenzo Alivi, an Italian hydraulics scholar, formalized the complex mathematics for slow-closing valves in the early 20th century. He gave engineers the tools to calculate the exact pressure curves if they extend the closing time safely.
He did. And the overarching lesson for the designer is this: never size your pipes, your welded joints, or your concrete pipe supports based solely on the steady-state operating pressure.
Right, because if a pump runs at 50 psi and you use 50 psi supports, you're setting a trap.
You must calculate the transient spikes from water hammer. When a pump trips offline in the real world, the water hammer will physically tear inadequate pipe supports right out of the concrete walls.
It is the invisible sledgehammer. Okay, so we've just talked about the catastrophic force water exerts when we try to stop it abruptly, but what's happening when we just try to push it steadily through a pipe?
It turns out the water fights back then, too.
Yeah, it fights the pipe walls and it fights itself. This brings us to the nightmare that is viscosity and viscous flow.
We now enter the realm of the Navier-Stokes equations.
Oh boy.
Yeah, these are the fundamental governing equations of fluid motion. They are essentially Newton's second law force equals mass times acceleration applied to a continuous fluid.
Okay, so what forces are we looking at?
They account for the pressure forces pushing the fluid, body forces like gravity pulling on it, and crucially, the internal viscous friction forces dragging it down.
The sources mention convective acceleration and vorticity in relation to Navier-Stokes. Can we translate that out of textbook jargon?
Of course. Convective acceleration represents how the velocity of a fluid particle changes as it moves through space, even if the overall flow remains steady over time.
Okay, give me an example.
Think of a wide, slow river suddenly squeezing through a narrow, rocky gorge. The water has to speed up as it enters the gorge. That spatial speeding up is convective acceleration.
Ah, got it. And vorticity.
Think of vorticity like a kayaker paddling down a fast river. If the water on the right side of the kayak is moving faster than the water on the left side, the kayak naturally spins in a circle. Vorticity is the mathematical measurement of that local rotation or spin within the fluid at a microscopic level.
Okay, that makes sense.
Because the Navier-Stokes equations contain complex, nonlinear terms for this convective acceleration and vorticity, they are famously difficult to solve. In fact, finding a general analytical solution is one of the Millennium Prize problems in mathematics.
But, engineers can't wait for a math prize to be won. We have to build things now, so we solve them for simplified cases, right? Like pure, perfectly smooth laminar flow.
Exactly. In a strictly laminar regime, viscous forces completely dominate. The fluid flows in perfectly smooth parallel layers, sliding over each other like a deck of cards without any lateral mixing or disruption. Right. When we apply Navier-Stokes to laminar flow in a circular pipe, the complex math collapses beautifully into the Hagen-Poiseuille formula.
And the Hagen-Poiseuille formula is a designer's dream. It proves that in perfect laminar flow, the pressure drop along a pipe is directly, linearly proportional to the velocity of the fluid.
Yep.
If you want to double the flow rate of thick oil through a pipe, you simply double the pressure from the pump. It is clean, predictable math.
But this brings us to the massive pain point we warned about in the opening.
Here it is.
The trap is misapplying the Hagen-Poiseuille formula to a flow that is not actually laminar. An engineer might calculate a pressure drop assuming perfectly smooth laminar flow, size a pump based on those clean linear numbers, and sign off on the installation.
And then what happens?
They turn the system on and the pump stalls out. It cannot move the fluid.
Because in the real world, flow is almost never perfectly laminar. It is chaotic. It is turbulent.
Exactly. And how do we predict if a flow will be smooth or chaotic? We use the Reynolds number.
The bouncer at the door.
The ultimate arbiter of flow regimes. It is a dimensionless ratio comparing the inertial forces, the momentum pushing the fluid forward against the viscous forces, the internal friction trying to hold the fluid's layers together.
Osborne Reynolds visualized this beautifully in the 1880s. He injected a thin stream of dye into a glass pipe of flowing water. At low speeds, low Reynolds numbers, the die stayed in a perfectly straight, crisp line. The viscous forces were strong enough to keep the water layers orderly.
Right.
But as he increased the speed, the inertia overcame the viscosity. The die line began to waver, then suddenly burst into chaotic swirls, mixing completely with the water.
And that transition point in a circular pipe typically occurs at a Reynolds number of around 2,320. Below that, the flow is kept orderly and laminar. Above it, inertial forces tear the smooth layers apart, and the flow becomes fully turbulent.
And once that flow goes turbulent, the clean math of the Hagen-Poiseuille formula is totally useless.
Completely useless. In turbulent flow, the pressure drop no longer scales linearly with velocity. It scales roughly with the square of the velocity.
Oh, wow.
So if you double the flow rate in a turbulent pipe, your pressure drop does not double, it quadruples. The friction skyrockets. Your pump has to work 4 times as hard just to fight the chaos inside the pipe.
So what exactly is that chaos? What is physically happening inside the pipe when it goes turbulent?
Well, it is not just random static. It is highly structured, multi-scale mixing. In turbulent flow, we see the introduction of what we call the Reynolds stress. In addition to the normal viscous friction sliding between fluid layers, you have microscopic erratic fluctuations in velocity in all directions.
So things are just crashing into each other.
Fluid particles are moving laterally, constantly colliding and mixing across the entire diameter of the pipe.
Ludwig Prandtl tried to explain this in the 1920s with his mixing length theory.
He did. Prandtl envisioned small parcels of fluid, or eddies, traveling a certain transverse distance, which he called the mixing length, before violently colliding with other fluid parcels and transferring their momentum. Turbulent flow is a physical mechanism of momentum transport.
Right.
Because these eddies are physically crashing into each other, turbulence is vastly more effective at transferring momentum, heat, and dissolved chemicals than laminar flow ever could be.
Let's visualize that. Turbulence is like a chaotic relay race. Massive eddies form in the center of the pipe, possessing huge kinetic energy. They break apart into smaller eddies, handing that kinetic energy down the line, breaking into smaller and smaller vortices, right down to the microscopic level where the fluid's viscosity finally acts like friction brakes, burning that kinetic energy off as raw heat.
That's a great way to put it.
But there is a catch. Right at the physical wall of the pipe, the party stops. The sources call it the viscous sublayer.
It is a critical boundary.
Yeah.
Even in the most violently turbulent flow, the fluid velocity right at the solid steel wall of the pipe must be exactly 0. This is known as the no-slip condition.
0. It doesn't move at all.
Right. Because the velocity must drop to absolute 0 at the surface, there is a microscopic, ultra-thin layer of fluid right against the wall where viscous friction completely dominates, forcefully suppressing all turbulence. This is the viscous sublayer.
If I am designing an industrial heat exchanger trying to boil a fluid inside a pipe, that sublayer sounds like a nightmare. It's like trying to scrape burnt milk off the bottom of a pot while stirring the top. The sublayer is stagnant.
It acts as an incredibly stubborn insulating barrier. The turbulence in the center of the pipe is mixing heat beautifully, but that microscopic viscous sublayer acts like a thermal blanket against the wall, preventing the heat from getting out.
So how do you fix it?
To improve heat transfer, thermal engineers spend their entire careers designing pipes with internal ridges, fins, or artificial roughness to intentionally disrupt and tear apart that viscous sublayer, violently dragging the turbulence closer to the hot wall.
Okay, so we've mapped out how fluids behave when they are trapped and pressurized inside a closed pipe. But when you rip the roof off the pipe and expose the water directly to the atmosphere and gravity, the rules change entirely. We are moving into open channel flow and the raw power of hydraulic jumps.
Yeah, when you remove the pressure boundary of a closed pipe, you lose the ability to push the water with a pump. You enter the world of open channel flow, where the fluid has a free surface exposed to atmospheric pressure.
And it's all gravity from there.
The entire flow is driven strictly by gravity, pulling the mass of the water down a physical slope. This dictates the engineering of everything from ancient Roman aqueducts to modern sewer mains, irrigation canals, and concrete flood control channels.
If we look at the historical data, the Romans were masters of this. They built aqueducts dropping only a few inches per mile over vast distances. But mathematically, calculating how fast that gravity-driven water will actually move is tricky, because you aren't dealing with smooth, pressurized pipes. You are dealing with rough terrain.
Right. Because the physical scales of rivers and large channels are so massive, the Reynolds numbers are incredibly high. The flow is almost entirely turbulent. Therefore, The friction holding the water back depends heavily on the physical roughness of the channel wall.
The sources point us to the Chizzy formula and the heavily utilized Manning equation. And the Manning equation relies on a specific empirical roughness coefficient, denoted as N.
The roughness is the defining variable here.
Absolutely.
If you build a smoothly troweled, perfect concrete drainage channel, your N value might be a very low 0.012. The water flows fast and efficiently. But if you were analyzing a natural riverbed choked with weeds, large boulders, and winding turns, the N value might jump to 0.05 or higher.
That's a huge difference.
It is. That coefficient dictates exactly how much kinetic energy is bled off as friction, telling you how fast the gravity-driven water can actually move.
And there's an incredible optimization trick hidden in the geometry here. If you are a civil engineer tasked with moving the absolute maximum amount of floodwater through a rectangular concrete trench, you don't just make the trench as wide and shallow as possible.
No, because you have to optimize what we call the wetted perimeter.
Okay, what is that?
The wetted perimeter is the linear length of the channel's cross-section that is physically touching the water. That surface contact area is where all the viscous friction happens. To get the maximum volumetric discharge for a given cross-sectional area of water, you must minimize that wetted perimeter. You want the most water touching the least amount of concrete.
And the math gives us a golden rule of thumb. For a standard rectangular channel, the optimal, most hydrodynamically efficient shape occurs when the water depth is exactly half of the channel width. If it's a 10-foot wide channel, you want the water running exactly 5 feet deep for maximum flow efficiency.
But open channels rarely maintain a perfect uniform slope. Hills drop off, rivers narrow, and spillways plunge. When the geometry changes, we must rely on the concept of specific energy in the Froude number to predict what the water will do.
Specific energy, right?
Specific energy is the total energy of the flow per unit weight, measured locally relative to the channel bottom. It is the sum of the potential energy, the water depth, and the kinetic energy, the velocity head.
And because total energy must be conserved, if the channel bottom drops suddenly or the walls narrow, the water depth and velocity must drastically adjust to maintain the energy balance.
Exactly, and the Froude number dictates the personality of that adjusting water. William Froude was a naval architect in the 1800s, and his dimensionless number is the absolute key to open channel behavior.
So what exactly is this number?
The Froude number is a ratio. It compares the water's actual flow velocity to the speed at which a small surface wave can travel through that specific depth of water.
Yeah.
If the Froude number is less than 1, the flow is slower than the speed of a surface wave. This is called tranquil or subcritical flow.
Okay, think of a deep, slow-moving, lazy river. If you throw a heavy rock into a lazy river, the ripples expand outward in perfect circles.
Right.
Because the water is moving slower than the wave speed, the ripples can actually travel upstream, fighting against the gentle current. The flow knows what is happening ahead of it because pressure waves can travel upstream to warn the incoming water.
That's a perfect visual. But if the slope steepens and the Froude number exceeds 1, you enter rapid or supercritical flow. The water is moving so fast, like rushing down a steep concrete spillway, that it outruns its own surface waves.
If you throw a rock into a raging spillway, you don't see circular ripples. The ripples are instantly swept downstream faster than they can expand.
The flow is completely blind. It cannot send any pressure signals upstream about obstacles or changes ahead.
Which sets the stage for one of the most spectacular and violent collisions in fluid mechanics, the hydraulic jump.
Oh, yes.
A hydraulic jump happens when rapid supercritical flow is suddenly forced to slow down. Maybe the steep slope of the channel suddenly flattens out. Because the rapid flow is blind and traveling faster than its own wave speed, it cannot smoothly transition back to tranquil, deep flow. It has to crash.
And it happens violently. The high-speed, shallow water slams into the slower water ahead of it. The water level abruptly crashes upward, creating a chaotic, churning, highly turbulent standing wave. Massive amounts of kinetic energy are destroyed in this rolling, frothing jump.
There is a massive pain point here for civil engineers designing municipal drainage. If you design an underground storm drain without accounting for the Froude number, you are asking for destruction.
Absolutely.
You might design a pipe thinking the rainwater will flow smoothly. But if a steep grade causes it to hit supercritical velocity and it suddenly hits a flat section, it triggers a hydraulic jump inside a confined concrete pipe.
And that jump violently expands, choking the pipe, compressing the air ahead of it, and it will literally blow heavy iron manhole covers right out of the street like geysers.
It is a destructive force, yes. But it is a misconception to think a hydraulic jump is always an engineering failure. In the right context, it is a vital, life-saving tool.
Definitely. A hydraulic jump purposely dissipates massive amounts of kinetic energy through extreme turbulence. Think about the spillway of a massive structure like the Hoover Dam or the Oroville Dam.
Millions of gallons of water rushing down a massive concrete face, possessing catastrophic world-ending kinetic energy.
If that rapid supercritical flow was allowed to hit the natural riverbed at the bottom of the dam at full speed, it would instantly act like a water jet cutter. It would erode the bedrock, scour the foundation, eventually undermine and collapse the entire dam.
So how do they stop it?
Engineers carefully design heavily reinforced concrete stilling basins at the bottom of the spillway, specifically to trigger a hydraulic jump. They intentionally create this violent crash to bleed off the kinetic energy harmlessly into the water itself, churning it into heat and noise before it safely enters the natural river.
I want to tie this back to something truly mind-bending. You look at the math of a hydraulic jump in a river, and you look at the math of a supersonic shockwave in a compressible gas like a fighter jet breaking the sound barrier. It is the exact same mathematics.
Yes.
A tranquil river is subsonic flow, a rapid spillway is supersonic flow, and the hydraulic jump is the literal shockwave created when the fluid hits the brakes. The math of a dam spillway is the math of an F-22 jet nozzle. Fluid mechanics isn't just a set of rules, it's a universal language.
It is a beautiful demonstration of how universal these governing equations are. The same physics apply whether you are dealing with liquid water or compressible air.
Up until now, we've talked about fluids flowing inside things, pipes or along channels, but what happens when you invert the problem? What happens when a solid object is forced to move through a static, heavy fluid?
Now we are looking at the aerodynamics of a car, the hydrodynamics of a submarine, or the wind loads trying to tear down a skyscraper.
Right. This is external flow, drag, and the deadly rhythm of vortex streets.
When an object pushes through a fluid, it violently displaces it, forcing the fluid to part and flow around its contours. This interaction generates two primary aerodynamic forces: drag, which acts parallel to the direction of flow, pushing the object backward, and lift, which acts perpendicular to the flow.
Let's focus on drag, the enemy of speed and efficiency. The sources break drag down into two distinct mechanisms: friction drag and form drag.
Friction drag is exactly what it sounds like. It is the direct shear stress of the fluid physically scraping along the surface of the body, confined entirely within that microscopic boundary layer we discussed earlier. If you have a long, incredibly thin, flat metal plate flying straight through the air like a blade, it experiences almost entirely friction drag. The air is just scraping along the metal.
But most things aren't flat plates. Cars, planes, and buildings are blunt. That brings in form drag, which is pressure drag. It is caused entirely by the physical, macroscopic shape of the object.
Right. High pressure violently builds up on the front nose of the object as it rams into the stationary air. And behind the object, a low-pressure wake forms where the airflow separates and spirals away.
So you have high pressure on the front, low pressure on the back.
The difference between the crushing high pressure on the nose and the empty low pressure on the tail effectively sucks the object backward.
Historically, understanding the separation was a massive hurdle, wasn't it? The sources highlight D'Alembert's paradox. In the 1700s, the brilliant mathematician Jean-Laurent D'Alembert used perfect, flawless mathematical equations to model an ideal, non-viscous fluid flowing around a sphere.
And his math proved that the fluid would part cleanly at the front, flow perfectly around the sides, and close perfectly behind the sphere, leaving zero pressure difference. Mathematically, in a perfect fluid, drag shouldn't exist.
But if you stick your hand out the window of a moving car, your hand gets ripped backward. Drag obviously exists. D'Alembert's perfect math didn't match reality.
D'Alembert's paradox highlighted the absolute, unforgiving necessity of including internal viscosity in our calculations.
Yeah.
Because real fluids possess viscosity, they experience internal friction.
Right.
As the boundary layer of air travels over the front of a blunt object, it loses momentum to friction. When it reaches the back half of the object, it encounters an adverse pressure gradient. The pressure is trying to push the air back toward the front. The boundary layer simply runs out of kinetic energy. It stops, peels off, and physically separates from the surface of the object.
That separation point is everything. When the flow peels off, it creates a massive, chaotic, churning wake of low pressure behind the object. That swirling void is the primary source of form drag.
Let's examine that wake more closely. The flow around a simple cylinder is a classic engineering benchmark. At extremely low speeds, low Reynolds numbers, the fluid sneaks around the cylinder and creates two perfectly stable, symmetrical little twin vortices right behind it.
It looks like two small whirlpools just resting there.
But as the speed increases, as the Reynolds number pushes past 90, things get wild. The wake becomes unstable.
What happens?
Instead of two stable twin vortices, the eddies begin to detach or shed, alternately from the top and bottom of the cylinder. One vortex spins off the top, creating a pocket of low pressure. Then one spins off the bottom, then the top again.
It creates a staggering, alternating pattern of swirling vortices flowing downstream.
Yes. This phenomenon is known as a Kármán vortex street, named after the brilliant aerodynamicist Theodor von Kármán.
And this alternating shedding is where the ultimate nightmare for structural engineers lies. Vortex shedding causes catastrophic structural resonance.
When a vortex sheds from the top of the cylinder, it creates a localized drop in pressure on the top, physically pulling the cylinder up. When the next vortex sheds from the bottom, the low pressure pulls the cylinder down. The cylinder is subjected to a powerful, alternating, cyclical, side-to-side force.
And the frequency of this alternating shedding, how fast it beats, is predicted by a dimensionless parameter called the Strouhal number, which relates the shedding frequency to the object's diameter and the flow velocity.
Exactly.
If that shedding frequency happens to match the natural harmonic frequency of the structure, say a tall industrial smokestack, a suspension bridge hanger cable, or a high-voltage power line in a steady crosswind, the structure begins to sway. And because the wind keeps beating at the exact right rhythm, like pushing a child on a swing at exactly the right moment, the sway amplifies.
If it goes unchecked, the structure will violently shake itself apart.
That is precisely what brought down the Tacoma Narrows Bridge on November 7th, 1940. The wind across the Puget Sound was blowing at a steady 42 miles per hour. That steady wind speed over the blunt shape of the bridge deck created a Kármán vortex street whose shedding frequency perfectly matched the bridge's natural torsional frequency.
The bridge began to twist and gallop wildly, eventually tearing itself to pieces in a matter of hours. It was a failure not of weight capacity, but of fluid mechanics.
To stop a structure from singing itself to death, you have to break the physics. You either have to stiffen the structure to change its natural frequency, or you have to disrupt the vortex shedding entirely.
That is why when you drive past a refinery or a power plant, you see long helical strakes, those spiral metal fins welded around the top 30 feet of tall smokestacks. They purposely break up the uniform wind flow, preventing the Kármán vortices from forming synchronously along the whole length of the stack.
It is an elegant aerodynamic solution. Now, there is another highly counterintuitive phenomenon regarding flow around a blunt object. Let us look at what happens at the critical Reynolds number. If you take a sphere or a cylinder and keep speeding up the flow, eventually, around a Reynolds number of roughly 3.8 times 10 to the fifth, the drag coefficient suddenly drops off a cliff.
Right. The drag coefficient plummets from roughly 1.2 down to 0.3. It is a massive, instantaneous reduction in air resistance.
But why?
What happens at this critical high speed is that the ultra-thin boundary layer itself, right on the front curve of the cylinder, transitions from smooth laminar flow to chaotic turbulent flow before it reaches the separation point.
Wait, if turbulence is chaotic friction, why is a turbulent boundary layer suddenly a good thing for reducing drag?
Because a turbulent boundary layer possesses significantly more internal kinetic energy due to all that microscopic lateral mixing we discussed earlier. High-energy fluid from the outer stream is constantly being mixed down into the slow fluid near the wall.
Right, so it has more energy to fight with.
Exactly. Because the turbulent boundary layer has more kinetic energy, it can fight against the adverse pressure on the back of the cylinder for much, much longer before it runs out of steam and is forced to separate. The separation point is physically pushed significantly further around to the back of the cylinder.
So the wake shrinks.
Precisely. The flow hugs the cylinder longer, so the chaotic, low-pressure wake behind the object gets vastly narrower. A narrower wake means a much smaller area of low pressure pulling the object backward, which translates to a massive drop in total form drag.
Okay, let me unpack this. You're saying that sometimes making a surface rougher intentionally trips the boundary layer into turbulence, which actually reduces the total drag. That feels incredibly counterintuitive for an engineer who spends all day trying to polish metal surfaces to reduce friction.
Yeah, no, I know it sounds completely backward, but yes, it is a deliberate trade-off. Polishing reduces friction drag, but for a blunt object, form drag is the vastly dominant force. You sacrifice a little extra friction drag to achieve a massive reduction in form drag. This is the exact applied science of why golf balls have dimples. A perfectly smooth golf ball would maintain a laminar boundary layer. The flow would separate early, leave a huge sucking wake, and the ball would drop out of the sky after 100 yards.
But the dimples change that.
The dimples intentionally trip the boundary layer into high-energy turbulence. This turbulent layer delays flow separation, drastically shrinks the wake, drops the form drag, and allows the ball to fly twice as far.
Fluid mechanics turning poor aerodynamics into a feature. It's brilliant. So we know how to cheat drag by manipulating the boundary layer. Now we have to look at the other major force, lift. Because the forces that give us flight hold a very dark, incredibly destructive secret when applied to liquids. We are talking about cavitation and system destruction.
Let us first establish the fundamental mechanism of lift. The sources point us to the Kuta-Joukowski equation. It states that lift equals the fluid density, multiplied by the uniform flow velocity, multiplied by the circulation.
And circulation is a mathematical measure of the overall rotation or spin of the fluid field around the object.
Right. It's easy to visualize with a spinning baseball. A pitcher throws a curveball, the spinning seams drag the air, creating circulation, and the ball experiences lift, curving sideways. But an airplane wing, or a pump blade, isn't physically spinning.
No, an aerofoil relies on its specific geometric shape to force circulation to occur naturally. It relies on the aquatic condition. A wing has a smooth, rounded leading edge and a razor-sharp trailing edge.
When the wing first accelerates from a standstill, the air rushing over the top tries to wrap around that sharp trailing edge to meet the air underneath. But the geometry is too sharp and the flow is too fast.
The flow cannot make the turn.
No, it violently separates from the sharp edge, spinning off a localized vortex, a starting vortex that is left behind, spinning in the air on the runway.
And nature abhors an unbalanced equation. The universe demands that angular momentum is conserved.
Exactly. Because a vortex was shed spinning in one direction, a mathematical counter-circulation of equal and opposite strength is instantly bound to the wing itself to balance the physical system. This bound circulation speeds up the air flowing over the curved top of the wing and slows down the air underneath.
Which brings us to Bernoulli's principle. Higher fluid velocity means lower pressure.
Yes. The high-speed air on top creates a zone of low pressure, and the slower air on the bottom creates a zone of high pressure. The high pressure pushes up toward the low pressure, resulting in a net upward aerodynamic force, lift.
It's pure physics magic. It allows hundreds of tons of metal to float in the sky until you get greedy and tilt the wing too far back.
Correct. If the pilot increases the angle of attack too far, trying to generate more lift, the air can no longer follow the steep adverse contour of the upper surface. The boundary layer runs out of kinetic energy, the flow separates completely from the wing, the low pressure zone collapses, and lift plummets instantly.
This is an aerodynamic stall. It is a catastrophic loss of lift, and pilots train extensively to recognize the buffeting that precedes it and push the nose down to recover.
Stalling is terrifying, but the real dark side of Bernoulli's principle isn't stalling an airplane. It's what happens when you apply these same aerofoil shapes to heavy, incompressible liquids. Let's talk about the absolute nightmare of cavitation.
Let's do it.
When an impeller blade inside a massive industrial water pump spins, it acts exactly like an airplane wing. It generates lift to grab and move the water. And just like an airplane wing, the water accelerates over the curved upper surface of the metal blade, causing the local pressure to drop significantly.
But water isn't air. If you drop the pressure of air, it just gets thinner. If you drop the pressure of water far enough, something terrifying happens.
Fluid thermodynamics dictate that if the local pressure drops below the liquid's specific saturation pressure, its vapor pressure, the liquid does not just flow faster, it instantaneously boils.
Wait, it boils at room temperature?
Right there, at room temperature. It phase changes from a dense liquid into a gas, forming thousands of tiny vapor bubbles on the low-pressure side of the spinning metal blade. This phenomenon is cavitation.
And boiling water sounds relatively harmless, until those bubbles move.
The problem is that the impeller keeps spinning at thousands of RPM. The water sweeps those low-pressure vapor bubbles past the blade and out into the main body of the pump housing, which is an area of much higher pressure. When those low-pressure bubbles hit that high-pressure zone, the vapor inside the bubble cannot physically sustain itself against the crushing force. The bubble collapses.
But it doesn't pop like a soap bubble. It implodes.
It implodes asymmetrically and violently. As the bubble collapses, it creates a microscopic, hypersonic jet of liquid that fires straight through the center of the bubble, slamming directly into the surface of the steel impeller.
And the pain point here is catastrophic pump destruction. Young engineers will get a panicked call from the plant operator saying their brand new, expensive industrial pump sounds like it's grinding a load of gravel. It sounds like marbles in a blender.
And the inexperienced engineer might think a bearing is failing, or that there is physical mechanical rubbing inside the housing. That is a fatal misconception. It is not mechanical rubbing. It is a phase change thermodynamic issue.
Wow.
Those collapsing bubbles are creating localized, microscopic shock waves, generating 100 to 200 atmospheres of pressure upon impact. They are literally blasting microscopic craters into solid stainless steel. Over a period of a few weeks or even days, cavitation can chew a beautifully machined pump impeller down to a useless pitted nub of ruined metal.
It blows my mind every time I think about it. Tiny little vapor bubbles popping can eat through a solid bronze ship propeller. It's like a billion microscopic jackhammers firing at the speed of sound.
To avoid destroying your infrastructure, you have to obsessively monitor the cavitation number. You must ensure that your system is designed so that the local dynamic pressure, even at the fastest point over the blade, never drops below the vapor pressure of the fluid you are pumping. You might have to physically lower the pump elevation to increase static head, raise the supply tank, or decrease the RPM to keep the pressure up. If you ignore the thermodynamics of Bernoulli's principle in liquids, cavitation will rapidly destroy your system.
Fluid mechanics takes no prisoners. All right, let's wrap this up. We have scoured the engineering forums, the subreddits, the late-night help boards where engineers go when the textbook fails them, and we are going to rapid fire through the top 3 most common questions professionals are begging for answers to online.
Let us address the realities of the field.
Question 1. We see this all the time in engineer posts. Why did my pipeline blow apart when the main pump shut off? I checked the math a dozen times. Every valve, pipe, and flange was rated for the maximum operating pressure.
Well, this is the textbook definition of water hammer, which we covered earlier. The static pressure rating of your pipe is entirely irrelevant when dealing with kinetic shock. When your pump shut off abruptly, perhaps due to a power trip, the massive column of moving water slammed into the stationary fluid ahead of it.
Right.
It converted all its massive kinetic energy into a localized pressure spike that traveled at the speed of sound up to 1,200 meters per second, rebounding backward down your pipe. To fix this, you cannot just buy thicker pipes. You must alter the dynamics. You must install surge tanks to absorb the expanding volume safely, or utilize slow-closing automated control valves to bleed the momentum off gently over a period significantly longer than the wave's round-trip time.
Moving on to question 2. Why is my incredibly expensive, perfectly factory-calibrated flow meter reading totally wrong when I install it in my pipe? The manufacturer says it's accurate to within 1%, but my flow rates are wildly off.
This failure comes down to ignoring the velocity profiles dictated by viscous flow. The flow velocity is not a uniform block across the diameter of the pipe. If you have viscous laminar flow, the velocity profile is a steep parabola. It is fast in the dead center and drop to 0 at the walls.
Okay.
If the flow is highly turbulent, the profile is much flatter, but still drops to 0 at the viscous sublayer. If your sensor probe is inserted only halfway into the pipe or placed too close to the wall, it is only reading the highly specific local velocity at that exact depth. It's not reading the average bolt velocity of the entire pipe.
So placement is everything.
Furthermore, you must ensure the flow is fully developed. If you place a flow meter immediately after a sharp elbow joint or a half-open valve, the turbulence is chaotic and asymmetrical. You must place the meter many pipe diameters away from any obstruction to allow the flow to straighten out and ensure the meter's internal software is calibrated for the correct Reynolds flow regime.
Last one, question 3. How do I stop my cylindrical temperature sensor probe from snapping off violently when I insert it into a fast-flowing river or a high-velocity steam pipe?
This is a classic manifestation of the Kármán vortex street. The fast, blunt flow is separating around your cylindrical probe, shedding destructive vortices alternately from side to side.
And it hits the resonant frequency.
Exactly. The frequency of this alternating shedding, dictated by the Stroll-Hall number, is inadvertently perfectly matching the natural, physical resonant frequency of your metal probe. The fluid is actively vibrating the metal to death through fatigue failure. To stop it, you must change the math of the system. You either change the physical diameter of the probe to forcefully shift the shedding frequency away from the resonant frequency, or, more commonly, you add helical strakes, small spiral ridges, to the outside casing of the probe. These ridges break up the uniform flow, preventing the Kármán vortices from forming synchronously, killing the vibration at its source.
The answers to the hardest engineering problems are always hiding in the physics. Next time you pour a cup of coffee, watch the way the stream breaks up as it hits the mug, or the way the steam forms chaotic eddies in the air. The exact same Navier-Stokes equations governing the milk swirling in that coffee cup are dictating the massive weather patterns across the globe, the aerodynamics of an F-35 fighter jet, and the blood pumping through your own heart. Fluid mechanics isn't just a brutal class you pass to get your degree. It's the hidden mathematical code of the universe.
Once you learn to see the math moving in the water, the physical world never looks the same.
If this helped you even a little, say something. We're putting this out for free, no paywall, no subscription, nothing locked behind a card. That only works if we know it's actually reaching people and doing what it's supposed to do. If you're a young engineer trying to figure this stuff out and this gave you clarity you weren't getting anywhere else, drop a like, leave a comment. It takes 2 seconds on your end, but it tells us this is worth continuing instead of just talking into the void. We are excited for your feedback, negative or positive.